everyone, I'm Onurcan, and today I will be talking about my term project. I will specifically talk about deep ordinal regression network for molecular depth estimation. So the first question is, what's the molecular depth estimation? Molecular or single image depth estimation is a very fundamental problem in 3D computer vision, and it has many applications in robotics or autonomous cars. This problem is hard since we have no stereo correspondences or any motion information, so doing single image depth estimation is not cheap, and it's very difficult since it's fundamentally an ill-posed problem. So consider this simple example. The two planes in the 3D space project to the same image in the camera. So giving this one 3D image, we can't reduce the depth information. There are infinitely many solutions to this problem. So to solve this problem, people propose many methods. A lot of previous work on molecular depth estimation can be categorized into two groups. In the first group, we have swallow methods, and the second group is the dip methods. In swallow methods, we extract handcrafted features from local patches, as in applied in a micro random field, for example. This is to enforce global consistency. And for dip methods, I can say that they outperform the swallow methods by a large margin due to their ability to learn a hierarchical and very complex features from a large number of images. And the main idea of the paper I selected for this term project is given here. So this is a classical scheme for deep methods. In this pipeline, the given input image is fed into a convolutional neural network in order to get a predicted depth map. And after obtaining this prediction, we compare with the ground truth depth map using a specific loss function, and then we can backpropagate error to arrange the network's parameters. And in this setting, there are two fundamental elements. The first one is the loss function. How can we choose this loss function? And most of the previous works actually use regression loss because the depth value is occurring as a continuous variable. But in this paper, they consider depth value as a discretized variable, and they apply ordinal regression loss. And they claim that this improved the results by a large margin. And in the prior works, other authors rely on progressively and stage-wise refinement of this cost function. And to get the final prediction, they did many refinements. On the other hand, in this paper, they just trained a neural network with high resolution output depth map by aggregating the multi-scale features, as you can see. And to focus on the first problem I have mentioned, how can we choose the loss functions? Probably the most widely used loss function is the MSE function. It's mean square error, and we just calculate the error on all the examples, but as pointed out in the previous works, the distribution of the different depth values is occurring as a heavy-tailed distribution. However, MSE loss is not robust to these outliers, and many works focused on designing more robust and better loss functions for this problem. So one of them, for example, proposed a MSE loss in log space, or one of them proposed relying on a mean absolute error, which is more robust. So all of these losses are designed for regression, but how about discretizing the depth values onto discrete depth bins and then apply classic classification network, for example? How about this idea? This was the first attempt of this paper, but since classic classification completely ignores the ordinal structure of the depth values, they finally decided to employ ordinal regression loss for this task. And to discretize the depth values, we should choose a method. A straightforward approach is to use an uniform discretization scheme, and here we have straightforward uniform depth bins. But as they pointed out, depth prediction uncertainty increases with the increasing depth value. To account for this issue, they propose an uniformly increasing discretization scheme, but in the log space. So, thus they allow larger quantization error for larger test values. And to implement the ordinal regression loss, they use a very simple method. They transform the ordinal regression into series of binary classification problems. So suppose we have three different ordinal labels from 0 to 2. Firstly, we will construct our first classification problem where the labels are determined by whether the ordinal label is larger than 1. So for the second problem, we state the binary classification problem as determining whether the ordinal label is greater than 0. So for k ordinal labels, we have k minus 1 binary classification problems, and they train their network by combining all of these binary classification losses and then do simple backpropagation. It's very interesting to see after they replace the regression loss by classification or ordinal regression loss, they actually improved the performance. And also one of the major contribution of this paper is multi-resolution architecture. They designed such a semantic understanding block. They use a pre-trained backbone network that is usually pre-trained on ImageNet. They use ResNet, for example, as a backbone. And using this backbone, they obtain the high-level feature maps. And on top of this feature map, they use dilated convolutions to get multiple scale features. They also have a full image encoder to encode the global information of the image, whereas these 4 convolutional branches on the bottom output the multi-scale features. So for the full image encoder in the previous works, they usually apply fully connected networks to directly transform the feature map to final feature map that has the same size as the input image. But in this paper, they claim that this is a very inefficient method, and they also claim that it has many parameters and difficult to optimize. Instead, they propose more efficient method to do this. First of all, they have a pooling layer that is used before a smaller fully connected network. After this, we have a fixed length vector, and for enforcing the global information, they do some further processing, and then they copy this single vector to all the pixel locations in the image. So by doing so, all the locations in this feature map share the same global feature information. And for multi-scale feature extraction, they use the dilated convolutions, which insert 0 to their kernels, and by doing so, they increase their filter sizes. In this way, we can have bigger kernels, bigger filters, without increasing the number of parameters in our neural network. For this technique, they actually influence from the previous works for semantic segmentation task. And so that was their method. It's a very rough summary of their method. So to evaluate their outputs, they of course use some metrics. For example, they use scale invariant log loss. It's basically the MSE loss in log space with some correction for the bias of the estimation. This makes sense since only relative depth values can be deduced from a given image without any X-ray information. So we can't deduce the absolute depth values without any X-ray information. They also use relative square error, relative absolute error, or RMSE. In RMSE, for example, they first reverse the depth values and then apply the mean square error. So this is some of the qualitative results on Kitty datasets. Their outputs have much higher quality with respect to prior methods, as you can see. This is some of their evaluation studies, as you can see. They tried applying the MSE regression method directly and MSE regression method with discretized beams, but their performances is very similar, as you can see. And we can conclude that quantization error is negligible, is very small in this task. And they also compared the loss function between the ordinal regression loss and multiclass classification, the classic multiclass classification. Basically, they concluded that ordinal regression is the best amongst them, and classification is better than direct regression. Also, the space increasing discretization is better than the uniform discretization. So it's interesting to see that their methods perform better than a regression network that is trained on MSE loss, even with respect to MSE metric. So I think this is really interesting. So we can say that their method also avoids local minima. And in this turn project, I reproduce this method for different datasets. First, I tried it on RGBD scenes dataset, and here you can see some of the outputs. Note that ground truth depth information is given only for the objects in this dataset, so we don't have any background depth ground truth information. Therefore, the ground truth depth estimation performance of the model may be very bad, and there are many sequences of videos in this dataset, and I split validation and training dataset by selecting only 2 sequences as validation set and others as the training set. I choose it this way because otherwise we would have memorization effects in our evaluation, and it wouldn't be fair comparison. And I also tried it on Kitty Carla, which is another dataset. Carla is a simulator, and Kitty is a well-known dataset in autonomous driving, but they actually test their method on Kitty, so I reproduce the results for Kitty Carla, which is a different dataset. And for both Kitty and Kitty Carla datasets, only the LiDAR scans are provided for depth information, and in this turn project, a simple linear interpolation is implemented to get dense ground truth labels for the training from these sparse lighter measurements. And to improve these methods, my first attempt was to use a different backbone topology. I tried two topologies specifically, ResNext and RegNet. In the original paper, they used ResNet, and ResNext was the best backbone. I also observed that hyperparameters related to feature depth or feature sizes should be carefully selected, otherwise we have very bad performance. And you can also see the quantitative results from these learning curves. And to decrease the error during the inference phase, we can also predict better discrete labels, specifically the means of the depth bins. With this strategy, errors are reduced since the conversion from discrete label to continuous label is more compatible with the dataset. So you can see the results on the figures on the right, but the differences are too small with respect to previous methods, so the effect of the improvement attempt is unclear to human eye. And for discretization, even more optimal strategy is to use k-means discretization. It's a very powerful technique for converting discontinuous data into discrete categories. And again, you can see some of the outputs for validation images. And I also compared this method with one of the fundamental approaches we learned in this course, which is K9 classifier. K9 performs worse in this task, but it also has some advantages. For example, K9 requires no training, whereas training deep methods requires too much time. But K9 inference phase takes much longer than the deep inference phase, even with an optimal search strategy. Once the deep math is trained, the training data is no longer needed to produce new predictions. This is also not valid for K9. But K9 is very simple and requires training only one parameter K. While the neural network training involves many hyperparameters controlling the depth or width of the neural network or its topology, its structure. So you can see the output for K equal to 1, and I also tried an Markov random field-based method in MATLAB, but it performed poorly with respect to these approaches, so I didn't include it. To conclude, casting the prediction task as an original regression problem increases the robustness. It can speed up convergence, and these methods perform better, and 3 different improvement attempts and their outputs are given. In the Storm project, those very intuitive attempts actually improved the results. Also, these deep methods is compared with respect to more fundamental machine learning approach, KNN, and KNN method is very simple and observed to have many limitations. It only performs reasonably if the training and test data are very similar. So here you can see my references. Thanks for watching.